Okay, welcome to physics class. Let's talk about waves. So, waves. Basically, you guys see them all around you. Right now, there are waves interacting with you. Can you name some kind of wave that is around you, interacting with you that you may not see, but wave that's out there?
Heat.
Heat waves? Yep.
Sound.
Sound waves? Yeah. I wasn't even thinking that one. Sound waves. Light
Radio
waves.
waves.
Go ahead, Coleman.
Radio waves.
Yeah,
Could be.
radio waves, your Wi-Fi signal, that's a radio signal.
Uh, UVE.
Yeah. Microwaves. See my microwave? A really bad joke, I know. But
Justin
that's what it is.
Hair has waves.
Wavy hair. Yeah, well, that's how wavy hair gets its name, from the shape of a wave. There's a squirrel right outside on my patio that I want to shoot and eat. That might be a video. You never know what you're going to get, guys. There's all kinds of waves, and waves are essentially made by some kind of vibration, which means a back and forth motion, right? Some kind of back and forth motion. Sometimes they call it, oh man, what was the word? Let me find it. A wave is made from a vibration or a back and forth. Oh, an oscillation. That's the word. An oscillation. When something oscillates, it goes back and forth, back and forth. So that's what you got. Now here's the main thing that a wave does. This is huge. What a wave does is a wave transfers energy. So a wave transfers energy. Let's use the example of a sound wave. And this might be a little disgusting, but it's really, really good. Have you guys ever had someone like whisper in your ear, and like you kind of have this nasty, annoying, like hot and moist, and it's like, don't whisper in my ear. You've experienced that? Okay, so imagine we're in our classroom. Put on your imagination caps, and you guys are seated in whatever seats you are, and I'm talking at you. What's actually happening is my voice is transferring energy to your ear, so you can hear my voice. The breath, the coffee breath, the moist breath that a person has does not flow from my mouth into your ear. Isn't that kind of nice? What actually happens is energy, right, hits the air molecules in front, and they keep bouncing off each other, and the energy gets into your ear. That's what's going on. It's not material transferring. It's actually energy transferring. So that's what a wave is. A wave is from a back and forth motion, an oscillation, a vibration, that's a term, and it transfers energy. Have you guys ever stood at the ocean and a wave comes and crashes up on your legs, and you can feel the energy smack you, but then the wave goes back, right? Think about it. It's transferring energy, but the water doesn't stay where you are. The water rushes back into the ocean. So that's what a wave is doing. It's transferring energy. It's not really moving material, okay? It's not really moving matter. So what I thought I'd do is I thought I would go live for a second outside. I'm gonna log my phone in, and hopefully this doesn't go crazy, and show you a back and forth motion. Okay, so I gotta log myself in. I had to log myself into my own meeting. Are you guys there?
Yes, sir. Very quiet, but yes.
He's muted. You're muted.
How about that? Can you hear me now?
Yes.
sir.
All right, good. So I'm going to switch the camera from looking at my crazy talking head to looking at my children's rope swing. Do you see the rope swing here? What's attached to the rope swing?
A weight.
Justin.
No.
Yeah, a weight. So I'm going to set this thing in motion back and forth. There we go. Back and forth. Back and forth. You're getting very sleepy, Coleman. All right, getting very sleepy. All right, so that right there is how a wave is actually made. Now, that might seem weird. Okay, Mr. Hicks, if a wave is made from something going back and forth, how is it that the wave actually has the up and down, curve pattern to it? You guys realize that most waves are represented by a sine curve? Do you guys remember that sine curve concept from math class? Give me a thumbs up if you understand that. Okay, good. I see Coleman's thumbs up. I'm going to assume everyone else. One of the things, I'm going live outside, so it might be hard for me to interact with all of you. But, oh, there we go, different view. Okay, but imagine underneath this swinging weight is a piece of paper, and we can pull that piece of paper underneath it, right? If this was dropping sand or making a mark on that piece of paper, as it's here, it makes a high mark, and then it swings down and it makes a low mark, swings up, makes a high mark, swings down, makes a low mark. And then as the paper slides this way, it actually would trace that curved path. You guys get that? Thumbs up if you are kind of following that. If you're not following it too well, there's actually a picture of a really old guy who figured it out and did it. We had a camp out this weekend. See the fire pit? And there's our COVID-19 quarantine room, just in case someone gets it. We were all set up. Okay, I'm just joking. I would really never quarantine my children to that, and I'm really not making a joke about COVID-19. I'm going to leave the meeting and go back in my room.
I'm back.
Yes, sir, you are.
Does that go okay? All right. So it's that back and forth that makes the vibration, and we visualize it with the up and down, up and down. So let me get a whiteboard out. And let's talk. Let's get the whiteboard out, and let's talk about some wave terms, or actually some wave, call it wave parts. Okay, so every wave has certain parts to it. Right. The first thing that I want to talk about is that waves have a high point and a low point, which are called a crest and a trough. Which one's the high point? Holly.
The crest.
So the low point would be the trough. Now, these are important. These are important concepts. Right? They're very simple concepts, but they're very important, because the height of the crest or the depth of the trough tells us something. So let's quick review. I'm going to put this up a little higher. What do waves do? They don't move material, but they
Transfer energy.
transfer energy. So thank you, Grace. That's a great answer. So since waves transfer energy, the amount of energy is going to have a relationship to the height of the crest or the trough. So if you have a very, very low crest, and then you compare that to a very, very high crest, which one do you think is actually carrying more energy?
The high crest.
The high crest. And then of course the same thing for the trough. And basically crests and troughs will match in size. So the crest is the high point, the trough is the low point. And so those are parts to a wave. So those kind of correspond to this characteristic. Those are parts, but I don't know if this is the right way to say it, but let's call this a characteristic. The concept of the amplitude. The amplitude of the wave is the measure of the height or depth of a crest or trough. And that amplitude, again, this is that concept, the height of the crest, the depth of a trough, the measurement of its amplitude is going to be a relationship to, it's going to have a relationship to the amount of energy that it carries. Does that make sense? So you've probably been to the lake or the ocean and you've been playing in the waves. Little 6 inchers, 1 footers, they carry a little bit of energy. But have you guys ever seen video footage of huge waves during a hurricane crashing up on shore? All right, well, those things are massive. And so they carry a much larger amount of energy. Okay, so now there is another characteristic of a wave. Every wave has a wavelength. That's actually the measurement of the distance of one wave. So you can actually measure it from crest to crest, trough to trough. Basically, it doesn't matter where you start measuring it from. It's just you have to stop measuring it at an identical point. So let's see if I can get a wave. That's not a good one. It's not perfectly symmetrical. I apologize for that. But essentially what we need to have is a baseline. I like to call it a baseline. Pretend that that's straight. The baseline is where you make all your measurements from for the depth of your trough or the height of your wave. So if you want to measure the wavelength, you would start here and go to an identical place. Would this be an identical place?
No.
Would this be the identical place?
Yes.
Yes, because right here, this is where the crest is starting to go up. This is where the crest is going down. We want to measure from the exact same place where the crest is starting to go up. Right. So you could measure from there to there. That's your wavelength. Now, let me see if I can hack back in here. There we go. Another important feature of a wave is its frequency. What does the word frequency mean? Just the regular old word. You don't have to use it in...
how often something happens.
Yeah, how often something happens. How frequently do you have physics Zoom classes? Twice a week. Right. So frequency tells you how often something happens. And so frequency is going to tell you how many waves in a period of time. And so that's actually measured in a unit called Hertz. Maybe it's Z. Let me check. Yep, it's Z. Named after a guy named Heinrich Hertz. I believe this guy was huge in helping to develop the TV and radio, because TVs and radios operate off of radio frequencies. So, you've got how many waves in a period of time. Okay, that's essentially what we call cycles per second. That's what Hertz is. How many cycles of waves are in a second? So let me try to draw a couple of waves. This wave has a certain frequency, right? You can see the number of waves that are in a certain space, and that would take a certain time for that wave to happen. So there, we just increased the frequency because in between this point, if we just measure from, successive locations, this point to this point, there's a significantly larger number of waves in that area. So your number of waves per second, your cycles per second is higher. So it's a greater frequency. So since again, waves are transferring energy, what do you think the relationship of frequency is to energy? If you have to, put yourself, go ahead, Coleman.
Higher frequency should mean a higher amount of energy.
Yeah, it should. And it typically does, right? So what you do is if you stop and think about being at the ocean and like one wave comes up and bumps into you every minute, right? Yeah, you got hit with a little bit of energy there. But if one wave comes up and hits you every 10 seconds, you got hit by how many waves in that minute? 6 waves. So, right, 6 waves in a minute versus 1 wave in a minute, you got hit with more energy because you got hit with more waves. So that's a very important concept for us to understand. Now, can I clear this page and go on to something new?
Yes.
Okay. All right. So I'm going to clear this page. And let's talk about wave speed. Every wave has a certain speed. Some waves travel really, really fast. Some waves travel much slower. For example, sound waves, you're looking at a baseline of 330 meters per second. Right. It's pretty fast. Light waves, 300,000 kilometers per second. Right. That's a whole lot faster. So every wave has its own speed, but the speed is going to be related to the wavelength, and it's also going to be related to the frequency. So frequency and wavelength have an effect here. So let's get the wave speed formula. It's maybe better to say velocity, but wave speed, wave velocity. We're going to use V for velocity. The velocity is going to be equal to the frequency of the wave times, that's a really bad X, times the wavelength. And this is a symbol for wavelength. It's the Greek letter. But the question is, who knows what Greek letter that is? Anybody know?
L, Y.
Candy cane with an extra leg.
That's a good description of it. It's the Greek letter lambda.
Yeah.
I don't know why they chose lambda. So velocity is frequency times wavelength. Probably can't use L because we use L for different measurements like measuring the length of an object if we're trying to get the area of something. Can't really use W because W looks like an omega symbol. And if you remember our circular motion chapter, we did use omega in that chapter, so can't use omega. So they went with lambda, frequency times wavelength. Now, is anybody wondering, okay, Mr. Hicks, if we're thinking velocity, typically velocities give us some kind of distance divided by a time period. So if we're in our car traveling to the grocery store, because that is allowed, and we're going 20 miles per hour, that would be 20 miles divided by hours, 20 miles per hour, right? Distance divided by time. There's a division sign there. If we're looking at this is multiplication. How on earth do we get a distance divided by a time? Well, remember, frequency is measured in hertz. Let's see, Justin, do you remember how I described hertz? It was something per something.
I don't remember. I can't think of it.
Can anybody help them out?
Amount of wave lengths in a period of time.
Yeah, waves in a period of time, or cycles per second, or waves in a period of time. Good. So cycles per second. I'm just going to put this here in as small of drawing as I can. Cycles per second. So then we multiply that times wavelength. Okay, well, what's our standard unit for always measuring length in physics class?
Meters.
Meters. So if we multiply these two units, will we get a distance over a time?
Yes.
Yes, we will. Because the cycles is telling us 5 cycles per second. So 5 cycles that are X meters long, we'll get a distance divided by time. So let's just crank this out. There's going to be some wave speed calculations in the homework assignments and probably on your test for this unit, but it shouldn't be too hard, right? Multiplication, division. Can you guys handle this type of formula?
Yep. You
can. You've been handling formulas like this all year. So here we go. What is the velocity of a wave if the frequency was, I don't know, we'll just go 20 hertz. Keep in mind, hertz is cycles per second, times a wavelength of 4 meters. What will the velocity be?
I believe that's 80 meters per second.
That would be correct. 80 meters per second. Any questions with that? It shouldn't be too big of a problem for us, I don't think. 80 meters per second. Now again, you can solve for any of these things. So let's solve this a little differently. Let's use a sound wave. A sound wave has a velocity of 330 meters per second. And let's use a frequency of, let's just go 260 hertz. And that will be multiplied by our wavelength, which is that lambda symbol. If we were to solve for the wavelength, the lambda there, right, what would we get?
330 divided by 260.
The answer is
1.2692. And I did that in my head.
No, Coleman, I think I saw you using your cell phone. How come that's not often in your locker?
Because my room is technically my locker now.
I got it. That's fine. You know, we're rolling with it. So 1.26 meters. Ooh, let's get that a little bit higher on the screen. That's actually legitimate, right? 260 hertz, that is actually very close to a certain note on a piano. And if sound waves are 330 meters per second and the 260 is a note on the piano, that would be the wavelength of that note. Isn't that kind of interesting to think about? If someone hits the note that's around 260 hertz on the piano, that wave is a up and down motion that's 1.26 meters.
That is pretty weird.
That is pretty weird. So there we go. Any questions there? All right, well, let me check my plans here because I think we're running out of time. And I think I've hit the majority of what I wanted to cover. So I think that's about good. Yeah, we've been on for 40 minutes. You guys have any questions right now?
No, sir.
No? Okay, well, I think...
I have a question, Mr. Hicks.
Okay.
I'm so sorry for just arriving to the party.
That's okay.
I definitely overslept because I was totally not cramming in work until 3 a.m. last night.
Yeah, that's okay. I recorded it, so I'll put the recording up at the same place where you found the link.
Thank you.
Okay, guys?
That sounds good.
Okay, what's your question then?
Yeah, just the recording.
Yep. I'll post that as soon as I can.
I didn't see the link for the physics class though. The only thing that's popping up on my class calendar is the link for the 3:30 Zoom class, March 30th, and then the
You have to
April
check the
7th.
new unit he put up on LMS.
I'm putting all the links in with the unit. So on the LMS, we've got this new waves unit. So you'll find it in there.
Waves and sound chapters. I see. Okay.
Yeah.
Yeah. Thanks.
You're welcome.
Okay.
All right.
Bye.
Okay. We'll see you guys later.
Bye.
Email
Yes,
me if you
sir.
have any questions. All right. Appreciate you guys. Have a good
Yes,
one.
sir.